In this video, we'll take a look at sample exercise 5, which we're asked to calculate the change in the standard entropy of the system, so the delta S, for the synthesis of ammonia from N2 gas and H2 gas. So that equation is shown here. So we have 1 mole of N2 gas, 3 moles of H2 gas will yield 2 moles of NH3 gas. So we're going to need those stoichiometric coefficients and also some values from this table here to plug into this equation. So this equation was given above in the worksheet, but I've included it down here to make it nice and easy so that when we plug in values, we know where they should go in this equation. So as mentioned, we're going to pull some values from this table below. So all of our values will be up here somewhere. So we have H2 gas, N2 gas, and then ammonia gas as well. So if we want to find the delta S for our reaction, it's going to be the sum of our products times their stoichiometric coefficient minus the sum of the reactants entropy values. So let's take a look at what that would look like. So delta S naught would give us, so for products, we have 2 moles of NO3 or NH3 rather, and the entropy for that in gas phase is 192.5. To save space, I'm not going to write the units, but it's joules per mole Kelvin. And that's the only product. So I'll put that in brackets. And then from that, we're going to subtract the sum of the reactants. So there's only 1 mole of N2. N2 gas is 191.5 joule Kelvin, joule per mole Kelvin from the table. And then we're going to add to that the 3 moles of H2 gas times their molar entropy of 130. 0.6. And again, that's joule Kelvin from the table. And now if we multiply, we get about 385 here, or exactly 385. And then I have 191.5 times 3 times 130.6. So that's 391.8. And if we subtract or 385 minus 391.8, we're going to get our, oh, I'm sorry, I forgot to add in our 192. So the sum of, oh, or sorry, our 195 here. So the sum of 195, 191.5 and 391.8, that's going to be 583.3. And this is the value we'll subtract from 385. So overall, we're going to see a negative entropy change of 198.3. And now I will write the full units, joule Kelvin. And that is our final answer. It's negative. And let's just take a minute to rationalize, should it be negative? So we went from 4 moles of gas over here to 2 moles of gas over here. So that makes sense. It checks out that there was a negative entropy change because we've halved the moles of gas from our reactants to products. So that brings us to some other kind of bits of information that have been outlined here about entropy and changes in the surroundings. So whenever heat flows in or out of our system, there's going to be a change in entropy of the surroundings. Specifically for an isothermal process at constant pressure, right? We'll box this all in here. The change in entropy to the surroundings equals the negative heat of the system. So remember that's of our reversible process divided by the temperature in Kelvin. And that's all at constant pressure. And we know that the Q of our system, the heat of our system, is simply delta H. And that's because it's happening at constant pressure. So we just equate this to this, and then we can plug in place of Q, delta H, like we did in that previous problem for condensation or vaporization, all of the phase changes. So there's another equation here that we include in the summary. The entropy change of the universe is the sum of the change of the system and the change of the surroundings. And the universe itself is composed of the system and the surroundings. So that's the entire known universe. And for spontaneous processes, we talked about this before, the entropy of the universe is greater than zero. That means that the entropy is increasing in the universe. And we know, therefore, that spontaneous processes are generally are irreversible because of this. So we'll continue next time with our next topic on Gibbs free energy.